Hi, so this is the second part of today's session where we will be focusing on using frequency analysis to generate sound responsive visuals. In the first video we looked at how to use amplitude analysis to do this, how to use the amplitude of an audio signal to control the properties of a three-dimensional object, and in this video we'll look at how to do this using a slightly more complex process of frequency analysis. Okay, and we will use this as a way of extracting a larger number of data streams from our sound analysis to control a larger number of objects. Okay, it's slightly more technically involved, but a lot of the principles mean are kind of the same really. We're looking at how strong signals are within certain frequency bandwidths, and using that measurement of the strength of a signal within a specific frequency bandwidth to control some property of a three-dimensional object in processing. Okay, so we're going to be looking at how to do sort of frequency analysis and use this to control visual objects. To do this, we're going to use a thing called a fast Fourier transform, or what I'll refer to as an FFT, okay, from here on out. And this is what does this is a process that breaks down a complex signal, so anything other than a sine tone really, that is made up of numerous frequency components. It takes that complex signal and breaks it down into its simple components, into its sinusoidal components, okay, and therefore shows us all the individual frequencies which, when added together, make up that complex signal. Okay, so it takes apart these complex sounds and tells us what they're made of in terms of frequency content, and then we can use that analysis data to control our visuals. So if we, for example, have a Nyquist rate of 22,050 Hertz, okay, then we break down that frequency range into 512 different frequency bandwidths, or what in the jargon of Fourier transforms are referred to as bins. And in this video I'll kind of flip between that terminology a little bit. Technically these different frequency bandwidths are called bins, but as musicians and creative practitioners, we're perhaps slightly more comfortable with thinking them as frequency bandwidths in the way that we might when we're using, say, like a bandpass filter or something like this. Okay, but if we have a Nyquist rate of 22,050 and we're breaking that down into 512 different frequency bandwidths that we want measurements on, okay, then each of these different frequency bands or bins would be 43.06 Hertz apart. Okay, so what does this mean? Well, the measurement sort of starts from 0 Hertz. So in the first bin we're sort of measuring 0 Hertz or DC offset. In the next bin, the center frequency, so this is a bandwidth of frequencies, okay, and what this value specifies is the center frequency, okay, in the middle of that bin that's being sort of looked for, and the strength of that signal being measured. So the center frequency of that bin will be 43.06 Hertz, okay, and then the next bin along, the center frequency of that, 86.13, the next bin, 129.18 Hertz, and so on. So we see these sort of multiples of 43.06, okay, because this is what we get when we divide the Nyquist rate of 22,050 Hertz by the number of analysis bins or frequency bandwidths that we're looking for, which is 512. Okay, and here I've just shown the values of the center frequencies for the first 9 bins, because you get the idea, and writing out 512 of them would be a little bit tedious. Okay, and so this is what we're looking for. Now, we saw a couple of weeks ago what happens when the frequencies being fed into a fast Fourier transform or a frequency analyzer sit somewhere between these bins, or aren't sort of exactly the center frequency. And we saw how the power sort of leaks out of the individual bin and sort of spreads across this sort of whole range, and so on. And a frequency that's sort of bang on the center frequency just gives a nice sort of clean line in the analyzer that we were using a couple of weeks ago. So it's not that the Fourier transform only reports on the strengths of these specific frequencies. A frequency falling between, for instance, 86.13 and 129.18, we're still going to get a sense of the strength of that signal, of that frequency, rather. It's just not going to be necessarily quite as clean, if you like, an analysis as this exact center frequency and, say, a sine tone at that precise frequency would be. Okay. And so, for example, if we were feeding a kick drum into our frequency analyzer, we'd expect to see plenty of signal in these first three sort of meaningful bins, but then the signal rapidly tailing off up in the higher frequency ranges. Okay, so the lower frequencies that we would associate with a kick drum would result in sort of a higher sort of measurements, higher strength signals in these first few frequency bands, and obviously much lower power or lower strength in these higher frequency bands. Okay. One of the reasons for using Fourier transform rather than just the amplitude analysis that we looked at in the previous video is that it gives us more data streams. Okay, whereas the amplitude analysis just measured the strength of the whole audio signal that was being played and gave us therefore a single data stream. The Fourier transform gives us information on the strength of the different frequency components of that complex signal, and therefore gives us a great number of different data streams that can be sort of selected and used creatively. Okay, and it also means that the kind of data that we're going to be getting is going to be more responsive to the different frequency bands of our sort of compositions. Okay, so we're going to get data that we can use corresponding to the low frequency aspects, such as kick drums or bass lines. We're going to get data that corresponds to activity happening, say in a melodic line or a higher frequency sort of pad or synth line, or cymbals that have lots of noise and so therefore spread, sort of wash over the entire spectrum, things like that. So it's going to give us more data to work with, which means that we can do more things with it, and we can take a more sort of nuanced and a sort of dynamic approach to the use of sound analysis data in our creative projects. Okay, so what we are going to do is start building up a project in processing. Okay, so let's open processing. Right. As with before, the first thing that we want to do is to import processing's sound library and all the functions therein. Okay, and we're going to want to set up a few variables to begin with too. Okay, so today we're looking at using fast Fourier transform. And I mentioned that the sort of acronym for this was FFT. So we want the FFT object from the processing's sound library, and we are here declaring that as a variable and giving it the name FFT. Okay, so we're asking for a FFT object, and we are using the variable name FFT for that to be referred to in the code below. I mentioned that we need to specify the kind of the size of our FFT. Okay, the number of frequency bands that we want to break down as a complex signal into. Okay, so if our Nyquist range is 2250, okay, if we're breaking it down into 512 different frequency bands, this is going to be more precise than if we broke it down into 256 bands, okay, because we'd have sort of twice as many frequency bandwidths that we were measuring, so therefore the analysis of the frequency content will be more precise, more accurate, but 512 will be sort of less precise than, say, using 1024 frequency bins and so on. But we need to sort of decide how many bins are going to be used, or how many frequency bandwidths we're going to be analysing. Okay, we're going to use a sort of pretty decent number here. We're going to use 1024 frequency bands to analyse. Okay, you might want to fine tune this and adjust it as your projects develop, because what you'll realise is you don't necessarily need the data from all the different frequency bands you're analysing. Depending on the content of the audio file you're feeding into it, there might only be specific bandwidths of frequencies that are really useful and relevant, and so you might want to kind of adjust these things. A thing to bear in mind is that this needs to be some kind of power of 2. So there are quite specific numbers that we might use for specifying the size of our FFT or the number of frequency bands that we're going to analyze. Okay, and here would be some common ones. Okay, right, now what we also want to do here is to import the sound file function from processing sound library, and we're going to use the file name there. Okay, so as a stored in a variable called file. Okay, and now we're going to set up the setup function. Okay, we're going to do the obligatory setting up the size of the window that we want processing to create for us, and here we need to tell it that we are going to be using 3D rendering as well. Okay, because of some of the things we're going to do later on in this tutorial about using the analysis to control things like size and speed of movement and color and so on, I'm going to change the default color mode from RGB to HSB, hue, saturation, brightness. Okay, and we'll see why that's necessary a little bit later on. Okay, when we come to manipulating the color of 3D objects. What we're going to do is just get the setup function working and check that our sort of we can import and hear our audio file and things first, and then we'll come back and start adding the kind of visual objects and so on. So what we want to do is initialize the fast Fourier transform. So we want to create a sort of new instance of an FFT, and what we need to tell it is the size of the FFT here, which is the variable bands. Okay, which we defined up here. Okay, so we're using 1024 bands. Okay, frequency bins, frequency bandwidths, however you want to think about it. Okay, then we need to load into the sound file player then an audio file that we want to use, and this would be your sort of pre-composed audio piece. Okay, or some kind of test file that you might be using now, just to start sketching out your visual sides of your project. Okay, so we're going to assign to the file variable a new instance of a sound file player, and we're going to put in there the file path to some kind of sound file. Okay. I'm going to finish just writing the setup function, and we'll come back and we'll adjust the file path and so on, so it points to actually to a WAV file that we're going to use. Okay. We're then going to ask the sound file player stored in the file variable to loop whichever sound file it has loaded. And then now this should be sufficient for creating the processing window, initializing the sound analysis here, for playing the audio file, and then all we need to now do is to patch the looping audio file into the FFT analyzer's input. Okay, so we do FFT input. What are we putting into it? We're putting in the looping file, the looping sound file that is being controlled here. Okay, so this patches the sound file being played into the FFT analyzer. Okay, so now let's fix this file path here. Okay, so the first thing I'm going to do is to save this project, Spectrum and analysis. Okay, and for convenience I'm just going to store it on the desktop here. Okay, so here's my project folder that the processing has created for me, and then in there I'm going to create a new data folder where I'm going to store an audio file of some kind. And so now I'm going to find an audio file on my hard disk that I want to use as part of this tutorial. So let's have a look in here, and this one will do. So I'm going to copy and paste this file into my processing project data folder. Okay. So here I have this pendulum sample, okay, file here. Important thing to note here about writing the file path is that the data folder is in the same project folder as the code that I'm writing here in processing. Okay, and so because it's in the same folder, I can specify the file path as dot, which means current directory. Okay, wherever this code is stored, then I can say it's in the data subfolder, and the file that I am looking for is called, let's have another look, pendulum underscore sample.wav. Okay, so that should be my audio file. So if I've done all that correctly and I run the code, okay, so here I have my blank window, and you can hear the sample looping. Okay, so we know that that's all working there. Right, the next thing to do, we're going to sort of need to kind of jump backwards and forwards a little bit between the draw loop, between the setup function and the global variables above that. And I'll try and do that in as clear and logical way as I can. So now let's set up the draw loop that we need to create the actual sort of visible objects on the sort of in the animation that we're going to make here. And we can set up some sort of standard things like background color, which will clear the window every time draw loops. I'm going to specify that no stroke be used. I think it just looks a little bit neater for what we're going to do today. And for now, I'm going to leave it at that, because we are going to jump back up and we're going to set up a few more variables that we're going to need to use here. Okay. So the first thing that we need to do, going back up here, is we need to create an array, okay, to store in the measurements of the different frequency bandwidths, okay, to store the strength of the audio signal within the different frequency bandwidths that the analyzer is listening for, okay. The FFT analyzer, the fast Fourier transform, is going to break down the signal, and it's going to tell us how strong the signal is within specific frequency bandwidths. What we want to do is we want to be able to store each of those measurements within a slot of an array, okay, so that can be pulled out later on and used to control visual objects, okay. So we are going to create a floating point array. We're going to give it the name spectrum, because it's going to contain a measurement of measurements corresponding to the spectrum of the audio file that we're using. And we can set it up now as a new floating point array, and the size of the array, the number of slots in it in which we can put and store objects such as numbers, is however many frequency bands we are analyzing, okay. So this is 1024, okay, so I'm using that variable there. So there's my an array waiting to receive the output of my spectrum analyzer, okay. So what I can then do is jump back down to the draw function here, and I'm going to ask the FFT analyzer to analyze whatever audio file it's receiving, which, as we defined up here, is the looping sound file. So we're going to ask it to perform an analysis of that and to store the analysis data, the measurements of signal strength within specific frequency bandwidths, within the spectrum array that we've just created. Okay, so it's going to analyze that sound and store the data in the spectrum array that we will use later on. Now, as I said earlier on, we don't necessarily always want to use every frequency bandwidth, okay? For instance, you know, I'm probably not going to be all that bothered in this project about, you know, frequencies from 18,000 hertz upwards and things like that, to say the least. So we can be a bit selective about the actual bins or frequency bandwidths that we want to draw upon and to use in our animations. Okay, so what I'm going to do is I'm going to create an integer variable, and I'm going to call it used bands. Okay, and this is going to allow us to say, well, actually, I only want information corresponding to the first 24 frequency bandwidths. Okay, so the lower range of frequencies. Okay, let's say here. So we're going to then sort of use that shortly to limit the number of bands that we're actually making use of. There's going to be a few other things that we need to set up here. The way we're going to use the Fourier transforms data is, in this project, for each of the bands that we're using, for each of the used bands, I want processing to create a three-dimensional cube, and then the strength of the signal in each individual frequency band is going to control the size, the color, the transparency, and so on of that object. Okay, and so what I need to do is I'm going to need processing to create, in this case, 24 different cubes, and to distribute them within the 800 by 800 window that we are creating here. Okay, so processing needs to know where in that window each of these cubes needs to be. Okay, we're not going to, in this tutorial, specify exactly where those cubes need to be. I'm going to sort of allow them to sort of be randomly distributed on the screen. But what we do need to be able to do is to have an array that's going to store the coordinates for each of those objects, the x and the y coordinates, saying where those things are going to appear on the screen. Okay, so for that reason we need to create a few more arrays. So some more floating point arrays. I'm going to create an array that stores the x coordinates of each of the cubes, each cube corresponding to one of the 24 frequency bands that I'm actually interested in from out of the 1024 frequency bands that are actually kind of being analysed. The reason for this combination of numbers, having an FFT size of 1024 but only using 24 of those bands to create my sound responsive visuals, is that this gives me quite a precise frequency analysis. The bands are relatively narrow and therefore quite precise, and I can choose just to use a small number of those that have a clear connection to the audio that they are responding to. Okay, so I'm creating this floating point array for the x positions, the x coordinates of each of the objects, which will correspond to each of the 24 frequency bandwidths that we are analysing here. It's going to be a new floating point array, and the size of that floating point array is going to be however many frequency bands I'm interested in using. And so this is the used bands variable here, okay, which I can just copy and paste in there. I now need to, of course, do the same thing for the y axis. So I'm going to have a floating point variable called ypos, and it's going to be the same size because it's got the same number of objects. And ultimately I'm going to want each of those cubes to be a different colour too. So I want to have another array which is going to store the colours of each individual object. Okay. As with the amplitude analysis example, that was the first part of today's session, okay, and that was in the first video for today. We needed to specify, for the purpose of the kind of mapping that we're going to be doing, what the maximum value we are expecting from our audio analysis, okay, because we're going to want to map the kind of, let's say, you know, on a scale of 0 to 1 type data that we might be getting from our audio analysis. We want to map that onto things like color ranges that are 0 to 255. Okay, so what we need to be able to do that well is to say what we think are the bottom, the sort of minimum and the maximum values to expect from our audio analysis. Okay, So we're going to set up another floating point variable, and I'm going to call it max and then power, because this is going to be the maximum level that I'm expecting from my audio analysis, for instance. And we're going to use this variable shortly, so we need to set it up now. Okay. Right. The key things here are that we've set up these a variable specifying the number of frequency bandwidths that I'm actually interested in using. Okay. And that this variable is used to set the size of two different floating point arrays, one for the x coordinates of the objects we're going to put on the screen and one for the y coordinates of the objects that we're going to put on the screen. Okay, and then the colors as well, but this is the kind of key thing to focus on just for a second. So going back down to my draw loop here, we know that the code within the draw loop loops round and round and round and round indefinitely whilst our processing sketch is running. So what we're doing is we're saying paint the background white, so it's going to give us a clear screen every time. We're saying no stroke, but I suppose we're never really going to have any stroke, so I could slightly improve this, and I could put it up here in my void setup. And then we're saying every time it loops, analyze the spectral content of the audio file that's being played. Okay. Now, what we then want to do is to extract the analysis data and use it to control the objects that we're going to put on the screen. Okay. Now we know, because we're going to be focusing on 24 frequency bands, that there's going to be 24 objects that we're going to be drawing to the screen here. Now I really don't want to have to write almost identical code out 24 times for this, so we're going to use a for loop to do this. Okay, and so it will start to become clear why we needed to set those arrays up at the top of the code before moving on to this section here. So we're going to set up the for loop as is kind of standard. Whilst I is less than the number of used bands, increment I. Okay. And then we can sort of go about sort of our drawing. Okay. Creating the objects that we're going to see on the screen. So each of the 24 cubes that I'm going to put on the screen, I want to have an individual color, and we specify the color of these things by using fill. Okay. Now the colors of each object are going to be stored in this colors array. Okay. There are going to be 24 different colors in this array. The value of used bands is 24. Okay. What we know about the for loop here then is that it's going to go from 0 up to 23, the 24 slots in the array. Okay. Each slot in the array corresponding to either, in this case, the color of a particular cube. Okay, so the value of I is going to increment from 0 to 23, and then it's going to go back to the beginning again and keep kind of incrementing up in a loop. Okay, so I can use it to index the values stored in the color array. Okay, and so to pull out those color values and use them to set the fill values for the objects that are going to follow shortly. Okay. Remember that we're using HSB here, so this colour value is going to correspond to the hue of the object. Saturation, highly saturated, or maximum saturation, maximum brightness. Okay. And I'm going to want to have the frequency analysis control the transparency of the objects. So when a particular frequency band is very quiet, or when there isn't much sound within that frequency band, I want the cube corresponding to that frequency band to become very transparent. And when there's lots of, say, 80 Hertz present in a certain frequency band, I want the cube corresponding to that frequency band to be very opaque and very clearly visible on the screen. Okay, so I want to scale the transparency in accordance with the strength of the signal in a specific frequency band. Okay, so the way we're going to do that is we're going to map whatever value is stored in the spectrum analysis array, which is storing all our FFT analysis data. Okay, so whatever value is stored in there, which is, we are expecting to be something between 0 and the max power variable that we declared above, and we want the output of that mapping to be on a range of 0 to 255, okay, because this is the numerical range we use by default for specifying color values. Okay, so this mapping here is saying map whatever value is stored in the spectrum array at this particular index, which is going to loop round between 0 and 23. So let's say it's 0.23. Let's map that value onto a range of 0 to 255. Okay, so we're saying we're expecting it to be between 0 and, in this case, 0.5 is going to be the incoming range of the values from the spectrum analysis, and the outgoing numerical range is going to be 0 to 255. So if the value stored in spectrum at index I is 0, then we will get 0 output. If the value stored in spectrum at index I is 0.5, which will be the maximum we'd be expecting, then the outgoing value will be 255, and anything in between would result in an object of differing kind of opacity. Okay, the eagle eye amongst you will have noticed the little error marking that processing has put here. It's got a little wiggly red line under where I've written colour, and just here at the bottom it says that this variable does not exist. I'm going, hang on, I thought I set that up. So I'm scrolling up the top here, and it's because I called it colours, not just colour. So I'm going to put that there. Okay, processing is now happy with that. We've put the mapping in there, and I'm putting in the corresponding closing bracket to close off the fill function here. Okay, so now we have a fill message which will correspond to each of the different 24 cubes that we're going to put on the screen in a minute. Now, what we remember from, hopefully from the previous sessions, is that when we put a three-dimensional object in a processing window, its position is inherited from things like translate functions above it. okay, rather than having the x, y coordinates specified as arguments for the function itself. Okay, so we're going to create a three-dimensional box. Okay, now the argument that the box does want is what size of a box would you like in pixels. Okay, how many say 200 by 200 pixels on each side of a three-dimensional box. Okay, so what we want to do here is create a box of a certain size. That would give us a 200 by 200, a box of 200 by 200 on each side. Okay, what we want to do is we want to have the size of the box change dependent on the strength of the signal within a specific frequency bandwidth. Okay, so that's going to require a bit more mapping. Okay, so we're going to map the data stored in the spectrum analysis array at a particular index, which we are expecting to be on a range of 0 to whatever max power is, onto a range of 25 pixels. Okay, so 25 by 25 on each side of a cube, so a very small cube, to a maximum size of 150, because we're going to have 24 cubes on a screen, on a window that's 800 by 800, so I don't want it to be so huge that they're all just sort of covering the entire screen all the time. Okay, so these are values we'll do for a start. Okay, so this means that the size of the box is going to fluctuate between 25 pixels and 150 pixels, depending on how strong the signal is within a specific frequency bandwidth. Okay, what we need to do is to put these boxes on the window somewhere, in the processing window. You'll remember that we set up 2 floating point arrays above to store the x and y positions of our cubes. Okay, our 24 cubes. The box creating function here receives the coordinates for each box from a translate function above it. Oh, sorry, I missed a little bracket off here. You can see that there's a little red wiggly line here. Okay, there we go. Added that on there. Okay, right, I'm going to say that last part again. The coordinates of the box object are received from a translate function, which needs to come above it. Okay, and this will position the center of any object following the translate function somewhere on the screen. Okay, we've got 2 arrays to store the x and the y coordinates of the objects that we're using. Okay, so I'm going to have the x coordinate of a box be set by whatever value is stored in the at a particular index in the xpos floating point array, and the y value will come from ypos. Okay, so this is where the coordinates for this particular box are going to be stored. Okay, now again, those of you who sort of probably be thinking, a number of you thinking, hang on a second, where are these actual coordinates coming from? Okay, we've set the arrays up, we now have functions that are indexing those arrays and looking for values in them, but there's nothing in the code yet that's actually storing values in those arrays. So that's what I'm going to do now, is we're going to write a little loop which puts coordinates into these arrays that can then be used to position the boxes or the 3D cubes on the screen. Okay? So I want the objects, the cubes, to remain in fixed positions in the processing window, and they're going to initially sort of change size and color depending on the strength of the signal in the frequency bandwidth that they correspond to. Okay, but they're going to remain fixed on the screen, which means that I only need to define the XY coordinates for those objects once, and because I only need to do it once, I can do it up here in the setup function. Okay, so I'm going to go up into my setup function here, and I need 24 x coordinates and I need 24 y coordinates. I don't want to sort of write those all out myself. I'm going to use the computer to sort of choose those using some random number generators. Okay, so we're going to set up a for loop and say that whilst I is less than the number of used bands, increment I. Okay. So now we're going to, as this for loop loops round, we're going to store some values in the x and the y coordinate arrays. Okay, so what we're going to say is assign to, in the first case, so as this loops around the first time, we're saying assign to the first index of the x position array. So here's the assignment operator. So put at index 0 in the first instance a random number. Okay, now the random number could be between 0 and the width of the window. Okay, and then we're going to ask it to do the same thing but for the y position. So the first time this for loop goes around, we're saying put at the first index, the first slot in the y pos array, a random number between 0 and the height of the window that's being used. Okay, remember that the random function, if we just give it one value, it goes from 0 up to that value. So just putting height in is the same as going 0 to height. Okay, if we wanted all the cubes to appear in the bottom half of the screen, for instance, we might go from height over 2 to height. Okay, but we want them sort of distributed around the screen in some way. We'll come back and finesse this slightly in a little bit. Okay, and I also want each of my cubes to have a color. Okay, so we saw here that we were specifying a distinct color for each of the cubes we're using. So as we are calculating XY coordinates for each individual cube within this for loop, we might as well use the same for loop to assign values to the color array. Okay, and we know that the color values to be used are between 0 and 255. Okay, so this is going to go whilst I is less than 24, store in the first index a random value between 0 and the width of the screen, store in the y coordinate array a random value between 0 and height, and choose a random color value between 0 and 255 to be used as the hue of the object. Then go back around and do that again for the second object, go around and do that again for the third object, go around and do that again for the fourth object, and so on, all the way up to the 24th object. So now we have a populated array for x coordinates, a populated array for y coordinates, and for colours, and so on. So now that when we are down here in our draw array, and whilst this for loop is going round and round, there's actually some data now in those two arrays that we are looking up. Okay. Now we're not quite finished with this yet, but what we could do is just run it at this stage and see what happens. Okay. You can see the presence of a little cube here and something pink off the side of the screen here. They're oddly clustered in the bottom right hand corner. So we think, why is that happening? Why is everything, if this, if the for loop here in the setup function is choosing random numbers between 0 and the width of the screen and 0 and the height of the screen, we'd expect it to be positioned sort of randomly, sort of fairly well distributed across the whole screen, not clustered right down in the very bottom of the screen. Why is this happening? The for loop is looping round and round. This for loop is in the draw loop here, okay? So this is saying for each of the 24 frequency bandwidths that we're using, specify a fill color and a transparency. Position an object on the screen at certain coordinates. Position a box at those coordinates, the size of which is dependent upon the frequency analysis being carried out. And then it's going to loop back and do that again for the same thing for the second box, go back and do that again for the third box, and so on. But because this is looping round and round, it's the equivalent of having lots of different translate functions, one after the other, whereby this is going to offset the center point of an object, and then those xy coordinates are going to be further offset by this transpose function, translate function, and again and again and again. Okay, and what this is doing is it's pushing all the objects down into one particular corner of the screen. Where we have these this kind of interference between things like coordinates or rotation values, we know that to stop that from happening, we need to push the matrix, then calculate the coordinates for the object that we're going to create, and then put the object on the screen at those coordinates. And then once we've done that, we can pop matrix to then go back and create the next one, to assign the next, place the next object on the screen at the appropriate coordinates. Okay, so this push matrix, pop matrix means that now the 24 cubes that we asked for are spread a little bit more throughout the screen in the way that we would have expected from a kind of random distribution, okay, rather than all clustered down in the coordinates, in the corner rather. Okay, so push matrix and pop matrix sort that out for us there. Okay. What we have here then is a kind of functioning piece of code whereby when we run the code, we get 24 different cubes appearing at different places on the screen, and each cube has a different color, and the size of each cube is being adjusted by the strength of the signal within the frequency bandwidth to which the cube corresponds. Okay, so let's just say, for the sake of simple arithmetic, that each frequency band is 10 hertz. Okay, the first frequency band is between sort of 0 and 10 hertz. The next one is between 11, 21, and so on. And each of those frequency bandwidths has a cube corresponding to it. The stronger the signal is within those frequency bandwidths, the bigger or smaller the cube's going to be, but also the more sort of opaque or transparent the cube is going to be as well. What we can do to this to start to kind of sort of finesse it a little bit. So if I run the code again, we've got a few cubes appearing down the very kind of edges of the screen. Okay, so what we can do is we can go and adjust the way that the coordinates for the objects are being figured out. So here the center position of each cube could be anything between 0 and the very edges of the screen. Maybe I want the cubes to appear slightly kind of sort of away from the edges of the screen. So I want to specify minimum and maximum values for my random number generator. Okay. I don't want to have to sort of repeatedly type out the same number necessarily, so what I am going to do is to create a variable up here. I'm going to call it sort of padding in terms of how far or how large the margin is from the edge of the window, and it's going to be 80 pixels. Okay. So here the object can be placed sort of anywhere as long as it's more than 80 pixels and up to whatever the width of the screen is. But that's still going to position some objects at the very right hand edge of the screen. So if I do this instead as width minus whatever the padding is, the objects are going to be placed anywhere that is kind of 80 pixels from the left hand side of the screen to anywhere that is 80 pixels from the right hand side of the screen. Okay, so what I can do is then just do the same thing for the Y values. I'm just going to copy and paste that over and then change height just there. And so when we run this now, the objects are further away from the edges of the screen. And what we can see as it's running is that certain cubes very clearly respond to different frequency bandwidths. We can see that this purple cube here very clearly responds to the very lowest frequencies where the kick drum is. We can see that a number of the boxes are responding to the kind of delay that's applied to the hi-hat and the clap, hand clap that's being used in the track. And we can see these objects that are kind of diagonal across the window here, responding quite a bit to some of the frequencies in the vocal melody. Okay, so we've positioned the objects in a slightly neater way on the screen. The cubes on the screen are changing their size depending on the vocals, but let's add a little bit more animation to this. Okay, let's go back down into the draw function here, and we're going to ask these objects to rotate around the y-axis. And you remember that we're dealing with cubes here, and we're imagining suspending a cube from a piece of string, and then it's rotating around the y-axis here. Okay. We'll remember from the previous tutorial that rotate expects a value in radians, but if, like me, you don't have a very good sort of intuitive grasp of radians, we can use the radians function to convert a value specified in degrees to radians to then be used for rotation. Okay, I don't want this to be fixed. I want this to be a changing value. So I want to use some kind of variable that's going to constantly update to change that, okay? So what I'm going to do is go and create that variable at the top here. So I'm going to put somewhere above my setup, float, angle, which by default will be 0, which is fine. And I'm then going to use that variable here instead of a fixed value for the rotation. So I'm going to use angle here. I'm going to have what we want to do is once all the objects have been positioned, they're going to sort of all going to kind of gradually be sort of rotating on the screen. Okay, so once it's put all the objects on, decided what size they're going to be, decided what color and transparency it's going to have, we're going to ask them to sort of ask the processing to rotate these things. Okay, so we're going to put angle plus plus to have that incrementally increase the value of the angle variable and therefore continuously rotate the object. Okay, now we know that we need this to be between up to 360 degrees on a circle, whereas at the moment this is just going to kind of keep increasing into the tens of thousands and so on. So we're going to use, as we did before, modulo 360 to keep that within a 0 to 360 range, which will then mean that that number makes sense to radians, which then in turn makes sense to rotate. Okay. Okay. We might want these things to rotate a little bit quicker. Okay, so this is at the moment incrementing by 1. We might have to have some kind of a speed controller that we want to adjust. Okay, so let's put another variable in, float speed, and let's have it go twice as fast. Okay, so what we want to do is change it from angle plus plus to angle plus equals speed. So this will now increment by 2 rather than just 1. So we'll see the objects rotate at different speeds. So at a faster speed. We could do something like have them move much, much quicker. Okay, so we can play around with the speed variable there a little now as well. Okay, that will do for now, in that what we've done there is we've taken a pre-composed audio file which is being handled by some Processing's sound file player and being looped. That pre-composed audio file is being fed into an FFT analyzer. The FFT analyzer is breaking down that signal and telling us how strong the different frequency components of that signal are. And it's doing so here when we ask the FFT to actually analyze whatever is plugged into it and to store the data from that analysis in the spectrum array. We're only interested in a relatively small number of those frequency bands, okay? And the number of those frequency bands we're interested in is kind of dependent upon the audio signal that we're feeding into it. Which ones create a clear or an interesting relationship between the audio and the visuals, and that's the kind of frequency, the range of frequency bands I'm interested in using here, okay? But for each of the frequency bands that I am using, I'm saying there should be a box that corresponds to each of those used frequency bands. The colour of that box will have been randomly chosen, but each box should have a different colour. And the transparency of that box should be set by the strength of the signal in a particular frequency bandwidth. Okay. The strength of the signal in that same frequency bandwidth is also controlling the size of the box on the screen. Okay. So as there's a big bass drum hit, the box corresponding to that frequency bandwidth gets larger and becomes more opaque, and therefore seems to be brighter. As the kick drum dies away, the box shrinks in size and becomes more transparent, and therefore appears to kind of fade along with the visuals. And the same thing happens for each of the different 24 frequency bands that we are analysing here. Okay. What keeps the code relatively compact is the way that we are using the for loop to do this, and to loop round and say, create a box with a particular colour of varying size and transparency, first for frequency band 0, then for frequency band 1, then for frequency band 2, then for frequency band 3, and so on, and keep looping round and doing that. Okay, and so this is where those 24 different cubes are created. And here is where we update the value of the angle variable, which is causing the cubes to rotate on the screen. Okay, that will do for today's kind of technical walkthrough. I will shortly send out details of when I'll be available online on the Blackboard Collaborate forum to discuss how you might sort of adapt some of these and make it a bit more interesting than some spinning cubes, and turn it into your own kind of projects. Okay, but that will do for now.